Oh yeah. Okay. Alright, I think we'll make a start, guys. The lighting in here is quite relaxing. I'm quite tired. I've been in labs since 8 this morning. I think some of you were in some of my labs. I am knackered, so I'm sorry if I feel a little low energy, but I'll try my best. It's been a long day. Oh yeah. No, it's okay. Just gonna, oh yeah, actually quickly, before we just start, I'm just going to grab the tutorial sheet, sorry. Should have done that, but I was reading like an idiot. Where does that live? Oh yeah, so I've only got one screen to play with today in this place, so if you've got the PDF of the thing on your phone or anything, please look at that, because I can't put it up, obviously. I've only got one screen, so I'll draw diagrams, but you know, my diagrams are shite, so you're probably best off having it in front of you. And also that means you can shout at me for getting things wrong, which is always very useful. Yeah. So 2 seconds, let me just download these and then I can put them up. Save file, yeah, cool, and then download, and then save file. Oh, Camus, why do you attract me so much? I have to... No, why there? Why there? That's just dumb. Why there? So stupid. Cool. That there. And then you go this side. Yes. Amazing. Okay. Right. So, let's start. Let's get going. So, I'm not really sure where you're at your lectures. I don't really know what theme this is. When I was doing the sheet, I was kind of like, is there a theme? I don't really know. So, I don't really know what the theme of these are. I guess they're just interesting fluid mechanic equations. So question 1, the first thing we've got is this tank of water. And I'm going to draw the initial depth of the tank as a dotted line. Yeah, and it says that we've got this is B and this is A. We've got the diameter of the tank. I assume it's circular, does it say? No, it's 10 centimeters wide into the paper, so I'll just draw that like that. So we've got this initial depth in there, and that depth initially is 9 centimeters, and we've got 24 centimeters here, and we've got 10 centimeters here, so these are the dimensions of our bulk of fluid. And we're told that the tank is uniformly accelerated. So when I draw accelerations, I'll draw them as double-headed arrows, 5 meters per second to the right. Okay. So we're pushing. The tank's going to move, and that's going to probably do something funky with the fluid. Hiya, come in. So what do we think is going to happen, really? Like, imagine dragging a glass quickly to the right. The fluid's going to tilt, isn't it? Yeah, and that's going to exert a pressure on this wall here. So we're going to get something that ends up looking a bit more like this in the tank. Okay. So we happy with the diagram? You understand what's happening? Yeah.
Sorry, I can't really see what is showing up.
Oh, it's really crap, isn't it? Sorry. That might be a problem with the projector. Let me see if I can. I got focus here, so hopefully that helps. Oh, yeah, it's too bright. I don't really know how to change that, sadly.
Okay, it's fine if it can't.
We could, yeah. Not the best, though. Let me see if I can turn down the light somewhat on this, and maybe that will help. Oh yes. Didn't help at all. So it just adjusts to this horrible brightness. I don't know what to do about that. Sorry. I'll try and draw a little bit thicker, but I use a mechanical pencil, so it's not. Does anyone have a pencil that's thicker, like a normal HB pencil? Does anyone have anything like that? Sorry?
Yeah, myself.
You have one? Ah, yeah, that would be better, because I can draw thicker lines with that without breaking them. Cool. Alright, so let's draw that again. Let's see if this makes a difference. Yeah, is that better? Can you sort of see that a little bit better? And the lines? Is that better? Better? Yeah? Let me rewrite these. So this is, 9 centimeters. I'll write bigger as well, so we can hopefully see a little bit better. Hi, come in. 24 centimeters. B and A. Is that a bit better? Is that okay? Yeah, okay. So we have this initial depth, which you can sort of see as this dotted line. It's flat, it's just a flat plane. And because it's accelerating, the water's being forced up into the side. And we're asked what's the pressure on this wall here, the one that's BA and then the width here, so this one, okay? So where to start? Oh, and we're asked what the water depth will be here. So what's this value here, which I think we'll probably call D1, and I think we'll call this D2 over here, just to add clarity, and it comes in useful later. So let me get my solution. Where are my notes? So we're dealing with acceleration, which means we're probably going to be dealing with something like the momentum equation. So that's what we're going to be looking at eventually. So the first thing we're going to do is consider an element of the fluid. Let's say this element. Okay, so this little strip here, a horizontal element. Okay, so basically I'm just taking a small bit to play around with and learn something about the fluid. Okay, so it's below the whole lot of the fluid. Oh yeah, come on in. So it's below the whole lot of the fluid. Yeah, we happy with that? Small little element, and that's got a height h, little h. Okay, can we see that? Sorry about the diagram's a little naff, but there you go. It's got a thing h, and we can say that there's a pressure on this side, P1. Again, I'll try and draw these as thick as possible. P1, and on this side there's another pressure, P2. Okay? So we'll see that? Sorry, I know it's not the best. The diagram's crap on there. Are you all with me, what I'm doing?
Is P2 atmospheric pressure?
Sorry?
Is P2, where is exactly?
Sorry, so like imagine, these are walls. Imagine, I've tried to draw this along the walls, right? I know it's not very clear because of the projector, but it's a bit clearer on the diagram I've got here. I wonder if I can turn this around, maybe that will help you see. Oh no, that's not going to help at all, is it? Actually, that's terrible. And I can see what you see though. Okay. So P2. So let's draw the control volume just out. So it's literally just a little cuboid of fluid inside, right? And I'm saying, so this is where P2 is acting, and it's in the fluid. So it's on the wall from the fluid. So this is where our little arrows are acting from that pressure, right? And I'm saying there's another pressure over here, okay? P1 acting this way. That's P1. And these two will be different because the depth of the fluid is different, okay? So I'm going to write a force balance equation. So remember, do you remember that pressure is force over area, right? So I'm going to write that the differences in this pressure is P1, P2, times by the width and the height. So remember, this is going to be the width of the tank, and that's there, 10 centimeters. Okay, and then this is the height, right? The height. So basically, I'm saying what's the size of this area here, this little area, and this little area, and I'm just taking the pressure difference between them. Why am I doing that? Because I want that's going to be pushing that way, and that's going to be pushing that way. Yeah, so we just force balances, and then we've got the pressure that comes from the acceleration. So that's defined by rho. Can you see that rho? Okay, rho, h, L, and W. Where L is this value here, so that's L. This is W, and in this case, it's that small value h here that we're using for that. So all this is the mass, right? Does everyone understand why that's the mass? Because the density, and then these three combine to create the volume. Okay, so this is mass, and then we're talking about an acceleration. So we've got the acceleration here. This is just F equals ma, right? So this is F equals ma. This is this is force over area. Sorry, this is pressure over times area. That's a P. Sorry, oh fucking hell. That's a P. That's an A. That equals a force, and this is M. This is A, and that equals a force, right? So I'm just saying that these two are equivalent. So this is the mass here. And this is about this control volume, not about the tank. That's crucial. Let me just check my notes. Note that the increased pressure is due to... No, that's not what I've written here. It's due to the depth of the fluid. Noting the increased pressure is due to the depth of the fluid we have. Yeah, so... we know all these values really here, apart from the pressures, right? So we can mess around with this, and in fact we can actually do some cancellations. We can get rid of these, which is nice. But it's probably is it a good idea to keep them in there? No, they go away anyway. So we know that the pressure increase on this side, this P1 pressure, is caused by this depth of the tank, and then there's a little depth here that causes the pressure here, right? Are we okay with that? I.e., there's a small increase of depth here that contributes to a larger pressure in this region of the tank, right? Because imagine, you got to remember that there's kind of like the tank's accelerating to the right, so the force of the fluid is pushing this way. So this pressure is to do with the depth here. Are we happy with that? Does that make sense to people? Yes.
So 9 centimeters is the height of the cube?
Originally, when before we accelerated the tank, we had the depth of the fluid was 9 centimeters. Okay, so that's the original depth. The new depths are D1 and D2. They're not very clear. So let me write this. So I'll write D0 equals 9 centimeters, right? D1 equals an unknown value, and D2 equals an unknown value, where D1 is greater than D2. Okay, does that make sense?
Yes.
We happy with that? Oh wow, that is not clear. I'm so sorry, guys. I'll try and fix that next time we come in. I don't really know how I'll do it, but I'll flag it with IT, and then it will never get done. So what have we got? We've got this. That's a force balance thing, and we're saying that the depth of these contributes to a larger pressure on this side. Okay, so I can write an equation that looks something a little bit like this, where I can say that P1 minus P2. And then remember, we've cancelled out this WH, so that's gone. We don't need that, but I mean it's kind of there, but it's not. And then rho, that's a rho g, the gravity times by the depth 1 minus d2, right? So this here is that P1 P2. Okay, that's what I'm saying here. Well, I mean that's what the equation says, but on my notes it's got a WH in it. So basically, I'm saying that the differences in pressure are to do with the differences in the depth, right? And this is telling me how much pressure is induced by that depth, right? Are we happy with that? With the way that equation reads? This is a factor that means that these depths contribute this much pressure. Right? Happy? Yeah, if we write, so now we'll substitute, we'll call this equation 1, this force balance equation, this is equation 2. If we substitute this in, we get that rho g d1 minus d2 is equal to, rho LA, okay? Is that correct? It is. And you'll notice higher, you'll notice that rho's here cancel out again. So we're left with G d1 minus d2 equals LA. And this is A, just so you're clear. Oh, that's not there. But that's A, that acceleration up here, that 5 meters a second. I hope that's obvious. So yeah, we've done that. And basically we can say that the difference in depths then is equal to LAX over G, which is the ratio of this acceleration to gravity. And when we plug, and we've got all these, right? Well, actually, no, we don't. Oh yeah, we've got all these. We've got L, we've got AX, and everyone knows G is a constant, right? We happy with that? So we can say that this value here is equal to 0.122 meters. And now this bit's a bit weird. It took me a little minute to get my head around it, but in the notes it just says by symmetry that this thing occurs. But you can kind of envision it that as the thing tilts, the left side is going to raise by how much the right side drops. Okay, are we happy with that sort of physical image in your mind? Because that's why we can say that half of this difference is contributing to the up, and the other half is contributing to the down, right? So this is half of this distance, and this is half this distance from that original plane we had. Do you remember we had that original cube, and the thing has tilted. It's moved up. The amount that it's moved up on the left is equal to the amount it's moved down on the right, but that is equal to half the distance, right? We happy with that? I know that's a little weird. Like when I saw that in the notes, I was kind of like, oh yeah, right. It took me a minute. So I just hope that's clear. So we know that, right? So by symmetry, we've got half of that rises up. So we can say that we've got d1 is equal to d0 plus half of the difference between d1 minus d2. Okay, so that's basically what I just explained to you. And remember that d0 was 9 centimeters, and we know this difference is 0.122. So when we put in the numbers, d1 comes out as 0.151 meters. Okay, are we all happy with that? Does anyone have any questions about how we did that? Yes. Yeah, sure. So this is just when it comes into your intuition a bit. If you imagine dragging a box of water to the side.
Is it double?
Sorry?
Is it always double?
Is it always double? It's not double, it's half. So the amount that the water is at a level, right, and it shifts as it accelerates, right? That's intuitive to you, yeah? When it shifts, the amount it rises up is equal to the amount it rises down, right? So those two. So the difference that we found, this value here, yeah, is double of one of these rises, right? Yeah, is that clear? Yeah. So we're saying that half of that distance, half of that differences in depth, is what gets added to this here. Yeah, we kind of okay with that? Okay. So that's how we find the depth. The depth of the bit on AB. So now it wants us to find the pressure on AB. Okay. So we're going to use the pressure area force for this. So I'm going to write an integral, and the integral looks like this: width, rho g, right? So width and rho g is the amount of fluid and how much it gets accelerated, right? And then I'm going to write this. That's an integral d1 0. So saying from the bottom to the top, I'm going to divide it into tiny little chunks, right? Of z. From the bottom to the top, do tiny little. That's a z, right? And we know that z here is. So when we do this integral, Can anyone tell me what this integrates to? Anyone?
Z squared divided by 2.
Yes. Z squared divided by 2, right? Divided by 2, and it's between d1 and 0, and then we've got this constant out here, well, this factor out here that makes it into a pressure through the units, right? So that's just an integral. So all I'm saying here is take tiny little chunks of this and add them up, right, to create the area, okay? And then each, because if you remember the way integrals work is take a tiny little slice, and then what's the pressure on that? Tiny little slice, what's the pressure on that? Tiny little slice, what's the pressure on that? And that pressure changes at each part of the depth, because as we go deeper, there's more fluid on top of us. So that pressure is variable, there's a gradient to it, okay? So all we're saying with the integral is add up all those tiny little differences, and that gives us our full pressure force, okay? So that's what that says. Are we happy with that? Yes?
We use G, not A, because we're just analyzing it vertically, right?
So yeah, because we're talking about the weight of the fluid. Okay, so this value here, the rho g, you can sort of interpret as the weight of the fluid, right? So we're saying lots of tiny little bits that wide and that much weight of the fluid on top of it. But as it goes deeper, it times the weight of the fluid by a bit more, right? So it adds a little bit more each time. Yeah? Yeah.
So Z is the depth?
Yeah, Z's depth, yeah. So yeah, Z is acting. I don't, like we said last week, I don't know which way it should be. I think it might be up or down. I forgot to ask about that. What?
How did you actually know that side was AB and not this side?
Because it's in the question. What? Why is it not on there? Oh yeah, so for some reason, okay, so that's interesting. So it's not on your diagram. I'm sorry about that. I don't know why that's not there. Yeah, that's bizarre. I'm sorry about that. That's dumb. Yeah, okay. Sorry, I didn't notice that. So I've got the questions and the solutions on the same sheet. So that's how I run through them. So, but my diagram for some reason has B and A, and for some reason your diagram doesn't. Sorry, I didn't know that. That's not really my fault. But
Someone asked over the answer, and like there was a big like a being week, and someone posted a new diagram.
oh, okay. Well, that unfortunately that's like one of those things you've got to be paying attention to. Sorry about that. I bet that was a very hard question to do then, wasn't it? I guess if you find the pressure on the other wall, that's still equally valid. You've still done the same operations. It's just on the other wall. You know, it would be the same distance. You just use D2 instead of D1, right? So, I mean, as long as you understand the concept of this and you've got it now, then it's not too big a deal if you did the wrong side. Okay?
I have a question.
Yeah, man.
Referring to the previous part where we got like D1.
Yeah.
I use the equation of theta equals tan inverse of theta equals tan inverse.
Use trig to do it, yeah?
Yeah.
Did you get the same answer?
Yeah, but I think it's like that. It's like half the distance is like it's the adjacent. It's the adjacent. The half the distance. Because like the midpoint is where the height is the same.
Yeah, the tilt will occur there, yeah. It's the pivot point, right.
I've got the same answer.
If you've got the same answer, mate, don't worry
I
about
don't know
it.
if it's like a coincidence or it's actually...
I don't doubt you would have achieved a coincidence there. You would, even in an exam scenario, right? So in exams, you guys wouldn't have done an exam yet in uni. But if you do an exam and you get the wrong number and you continue with that number, then you'll still get most of the marks. If you get it's more about generating an understanding of what you're doing than actually showing the right numbers, right? That's why I skip the numbers most of the time when I'm doing this, because it's more important that you understand what we're doing, not the numbers that go into the equations, okay? So if you're in an exam and you did that and you got a number for depth, and then you continue to do this with that number, you would still get all the marks for doing this. You would just lose the mark for getting the number wrong, right? So it's not a big deal. You wouldn't lose all the marks, right? So if I can't conceptualize in my head at the moment whether that's always the way to do it, but if it works, right? I doubt you would have got a coincidental answer, right? Yeah. Okay. Is there any questions about question 1? Can I move on? No? We're okay. All right. We'll go to question 2 then. I want to get to question 4. Question 4 excited me. It's quite fun. It's like a proper mathsy boy. Yeah. What's up?
You didn't get the answer to part B.
Did I not give it? Oh, just sorry. I keep forgetting to put the numbers in. The number is it's 11.2 newtons. Right, it's on the sheet, but it's 11.2 newtons. That's what you get out of the arse end of that, I think, unless I've got that wrong. I see you quickly going to your. Oh, I didn't even write it on my old notes. Yeah, it says it's 11.2 on the solution sheet. So you would have just put the values in there. Oh, sorry. So yeah, d1 goes in here, right? So it's d1 squared over 2, okay? Because this is d1, and remember this sort of notation is saying what you're putting in the integral. So it would be d1 minus 0 over 2 that goes in that bracket bit, but because that's 0, it just goes to nothing. So and then w rho g. All right. So that's just what you do with the integral. That's what that notation means. All right. And then you just plug in the numbers. You've got them all, right? We calculate d1 in the last part. Okay. Right. Question 2. Where is my notes? So we've got this groovy petrol pump, and it fills 75 litre tank in 1 minute and 10 seconds. So we've got 75 litres. It's irrelevant that it's petrol, I think, in this question. 75 litres, and it's 1 minute 10. Does anyone 1 minute 10 is 70 seconds? No point asking that. Does anyone know what the conversion between litres and what units do I want here? And meters cubed is? Does anyone?
1,000.
Sorry, what? Hands, please. Yeah.
Divided by 1,000.
Yeah. So we're gonna. So this is going to be 75 times 10 to the minus 3 meters cubed. Okay. So that's just to trip you up for no real reason. Okay. So and then we know the pump exit. So we got this little pump, and the diameter of that pump exit is 3 centimeters. Okay. Yeah, what is the average pump flow exit velocity in meters per second? So that meters per second part is saying, hey, by the way, I put it in liters, you need to convert it. And we're going to need to convert this to meters, actually, so if I can remember my conversion factors. There we go. So the volume flow rate of the pump is equal to, so volume flow rate, right, is equal to the amount of liters coming out divided by the amount of time, okay? Because this is a volume. Litres is a volume, and the time is given to us at 70 seconds. Can you all see this okay? Sorry, I know it's awful. Is that clear enough? If you need me to write something else, if you need me to write something so it's legible, please tell me, because I won't notice otherwise. So we've got 75 times 10 to the minus 3 over 70 seconds, okay? So that's meters per second, right? Well, no, it's not. It's meters cubed per second. So that's our volume flow rate. How much volume of fluid is leaving the pump at a certain time? And that comes out at 1.07 times 10 to the minus 3. Okay? So that's how much volume of fluid leaves the pump per second, right? But another way to write the VFR is as the area times the velocity, right? Got an area, how much is going through it per bit, right? Yeah? Happy? So these two are equivalent. And the area is equal to, remember we're trying to find, this is what we want, right? This is what we want. So the area is pi, and it's r squared, and we've got the diameter, so it's 3 times 10 to the minus 2 over, right, just check I've got that right, because otherwise I feel like an idiot, over 2 squared times u, because and this is what we want, remember, we want u. And again, that's equal to this up here. So we can just write that they're equivalent, 1.07 times 10 to the minus 3. Okay? So then it's just a case of rearranging. That's all you got to do. That's literally it. Plug your numbers in, rearrange, and you get the answer to be 1.52. Okay? That's a really boring question, but you know, it's important to understand what volume flow rate is. Are we happy with that? Are we happy with what I've done? Yeah? So I said, we're given the volume flow rate because it says this much leaves by this much time. Cool, that's what the question's basically saying. And we also recognize the volume flow rate is area times velocity. Okay? So how it's flowing through that small, there's a circle and there's a amount flowing through it. And then we equated them, rearranged the equation to get u isolated, and it came out as this answer when we put the numbers in, alright? Yep. Okay, question 3. So question 3 is, what time are we on, how are we doing? Ooh, we might not get to the end of this. Question 5 is pretty easy. Oh, there's a 6th question. I didn't do question 6, guys. I'm sorry. I've been chock-a-block today, so I don't know. Look on when the solution sheet comes out. Look at question 6. Sorry, but we'll do question 4 because I think it's cool anyway. Yeah, sorry about that. I've been really bloody busy these last couple of days, and it's been sweeping me off my feet. Figure 3. So we've got this kind of mixing thing. It's a mixer. It's a big thing. Just mix in there. And there's a flow going in, that's number 1, and there's another flow going in, and that's number 2. I'm not going to draw them as pipes because it's a bit of a nightmare, but they are pipes, right? And they're mixing. What are they mixing? Well, first off, we know the pipe diameters. So the diameter of 1 is equal to 2 centimeters. Okay, and the diameter of 2 is equal to, I think, 3 centimeters. I think that's what I read. And pipe 3 has a diameter of 4 centimeters. Diameter of 3 is equal to 4 centimeters. Cool. Through section 1, we've got alcohol, right? Alcohol, I'm going to write alk, with a specific gravity of 0.79, right? And that's coming in, U1, this is 1, write that there. And U1 is equal to 8 meters a second. Okay, and then through pipe 2, we have water, which has a specific gravity of 1. And that's coming in at 6 meters a second. So U2 is equal to 6 meters a second to the minus 1. And we're saying, assuming that the two fluids are thoroughly mixed within the chamber, i.e. that they are now homogeneously mixed, and therefore their specific gravity kind of mixes up. Calculate the exit velocity and the specific gravity at section 3. Okay, so coming out of the pipe at part 3. So fluids that we deal with in fluids 1 are incompressible, right? So we can write that their volumetric flow rates are the same because of the continuity equation, right? What comes in must go out. What comes in must equal what comes out, okay? So as we, what are we doing? So we can write this. A of 1, the area of the pipe at 1, times U1, remember that was our volumetric flow rate that we did up here. Is it plus? Yeah, all right. Plus A2, U2, so that's what's coming in, so in is equal to what comes out, which is area free, U3, okay? Out. Right. So then we can just rearrange that equation. So we can figure out the area because we've got these diameters. So all the areas are known, and we've been given 1, 2 velocities, right? So the only thing we're going to find is the velocity coming out. So we rearrange this equation to isolate the velocity of 3. So essentially, it's I'm going to write in, but assume it, but you know that's that. In divided by A3 equals U3. Okay. So I've just not bothered to write that bit out again. So we write that and literally plug the numbers in, do what you got to do, and that comes out at 5.375 meters a second. 5.375 meters per second. Okay? Happy? Yeah.
Should we multiply by density too? Density, you're looking at the volumetric flow rate. Volume doesn't equal AU.
The volumetric flow rate tells you. Well, we're saying that there's continuity because the fluids are incompressible, right? So there's no extra space being generated. And you can assume that this whole system is full. So anything coming in is pushing something out the other end. So we only actually need to consider the small slices. And those small slices don't factor in you don't really need to...
Yeah, but volumetric flow rate usually equals velocity times...
area. You're thinking of mass flow rate, I think. Mass flow rate is rho AU, which is what we're going to use next.
Oh.
Yeah, so this is volumetric flow rate. It's talking about the size of the fluid, right? And you can assume that it's just anything coming in is going to push something out, right? So you don't need to know the densities of the fluid because it's not about the amount of fluid. It's not about like the amount of particles that are coming in and going out. It's about the physical size of the fluid that's going in and going out, right? So we're saying, like, imagine like just cubes, right? And those cubes are pushing in. Equal size, well, a cube that is the same size as both of those little ones has to be pushed out because there's no space. Does that make sense? Yeah? So now when we're going to calculate the specific gravity, we do need to know the densities for that, right? And that's from the mass conservation law, which is what you were saying, is the densities are involved in this point. So again, we've got the in-out equation that says rho 1, A1, U1, this is what you were saying, plus rho 2, A2, U2 in is equal to the mass flowing out, right? Because we've said that the volumetric flow rate has to be the same, so now we're considering the densities of the inside of those volumes, and therefore the mass within those volumes. Okay, and this is out, right? So it's basically the same thing that we've done there. This is A. Again, we want to find out what the density is in free, because from the density we can figure out the specific gravity, can't we? It's just the ratio of that and water. So you rearrange this. Rho free equals in over A free, oh, that's a free, U free, and that comes out at 922, which is quite close to water, I think, kilogram meters minus free, and that gives us, and you know how to do specific gravity. That gives us specific gravity of 0.922. We happy with what we've done there? If you're confused, please say. We're going to move on to question 4 now. But we all happy? Okay. Question 4. So this one's quite cool. I like this one. We're given this fat old description, but it wants us to build an equation. So this is interesting because it gives you an insight into how maths is built and how we derive these systems as we go. So I hope I do it justice because I quite like this one. So we've got a tank. The tank is not a battle tank, it is a tank filled with air. And that air is at a density of 1.2 kilogram meters to the minus 3. And it is at a pressure of 100 kPa. Okay? And it's been evacuated by a vacuum pump. Why have I written 1 meter cubed? What do I mean by that? What do I mean by that? What do I mean? Yeah, so in the equation it says that the tank volume is 1 meter cubed. So the volume of the reservoir is 1 meter cubed, okay? And the pump evacuates 0.0013 meters cubed of air per second, regardless of pressure. So the pressure is irrelevant to the evacuation of the air. The pump is doing all the work. Okay, so we're saying that Q, the flow of is that mass flow rate? No, that's volumetric flow rate, is 0.00. So this is VFR is equal to 0.0013 meters cubed. Okay, so that's what we're given in the question. Do we need to know anything else? The process is isothermal. So, and as a result, they're written as D's in this question, but they're supposed to be rows. I think this is an old question before, for some reason, they could put in rows into Word. But yeah, D stands for density in this case in the tutorial sheet. It took me a little bit to figure that out. So yeah, the process is isothermal. What does isothermal mean? Can anyone tell me?
Temperature doesn't change.
It's not pressure. It's another thermodynamic variable. Yes, temperature. Temperature doesn't change. Isothermal, right? Did you say Did you say temperature?
Yeah.
Oh, sorry, I misheard you. I thought you said pressure. My bad. I'm sorry. Your face was like offended, and I was like, "Oh no, I'm so sorry." my ears aren't what they used to. Like 15 years of metal gigs don't do them any justice. Yeah. So isothermal process means that we can relate the density pressure ratios to each other, and also that these are constant, right? If you will learn about that in thermodynamics. I can't remember if you do thermodynamics this semester or next semester, but stuff like that is thermodynamics, right? Just take the word for the question for it. That's why it's given to you. And we're asked to derive an equation that shows how the pressure inside the tank, P, changes with time, T, and then use it to calculate the time needed to reduce the tank pressure to 1 kPa, right? So currently we're sitting at 100 kPa, and we want to know the time, given that this pump is just evacuating whatever it feels like forever. How will it go down to? How long will it take to go to 1 kPa? Right. So we can say that P1 equals 1 kPa. Okay. Let me just make sure. Let me just read my notes quickly. Change the time. Blah 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 blah. Yep. So this system is not a steady system. It has a variable density. Okay. So we need to. That's crucial for us to remember. The continuity equation in this case is a little bit different. Basically, we can say that the continuity equation is the mass flow in. This is. Why do you call it the continuity equation? Surely it should be the mass conservation equation. That's strange. I think this is supposed to be the mass conservation equation, not the continuity equation. I think that's wrong. Yeah. Basically, we're saying here that the mass flow in minus the mass flow out, so this is a little bit of a different way of writing it, yeah, is equal to the rate of increase of mass. Okay? That will be a units balance thing, right? That's why that works out the way it does. But that allows us to write rho q. Remember the last question, wherever that's gone on my notes. I think it's on the back, isn't it? No, somewhere it's disappeared somewhere. Where's that gone? Oh, here it is. Remember that when we did this question, the mass flow continuity equation, so the mass conservation equation, was literally the volumetric flow rate equation, the continuity equation, with the rho's added in. Okay, so when we have this value here, which is Q, which is our volumetric flow rate from the pump, yeah, we can write rho Q, and that means our mass flow rate. Okay, we happy with where I've got that from? What rho Q means? Yeah. Okay. Cool. Where are my notes? There they are. Yeah, so we're saying that. So we've got nothing. Nothing's flowing into the tank. The tank is being drained of its precious air. Out is that mass flow rate, which is this. I'll write it like this. That's mass flow rate. That's what it usually looks like. Mass with a little dot on it, meaning the time derivative of mass. Right, and then the rate of increase of mass. So that's this part of the equation. I'm going to write that as RIM, and that equals the volume times by the change in density with the change in time. Okay? The rate of increase in mass. Are we happy with what that means? Change in density with a change in time times the volume tells us how much mass is changing, the rate that the mass is changing in the tank. Okay, so in this case, this value will end up being negative because the tank is being drained, but it won't necessarily be negative. It's just in this case it's negative, right? Because if you think about, let me write the equation, you'll see what I mean. So in we've got 0, right? That's this part. In we've got 0. We've got out coming out that, and we've got d, that's a rho over dt. Okay, so that's the balance of that. So remember, this has units with time, right? It's this should be per second, I think. Yeah, it is per second. That's probably why that's quite confusing. It's per second. Okay, sorry, I missed that off. But yeah, that's what that volumetric flow rate is. It's amount of volume per time, right? Look at the units. So this has time in it, and this is with respect to time, and therefore it gets the time units in it, right? And because this is underneath, that gives us an S-1 as well. So you can see how these balance, right? Because if you times the volume by this, you're left with kilograms, and if you do this times this, you get kilograms left over in the units as well, right? I think that's right. Oh, kilograms per second or something. Yeah. Right. So all I'm going to do is I'm going to do a little bit of rearranging. I'm going to bring the rho over here. So we have we'll leave the minus sign on the other side. I'll turn that into an equals. Minus q dt. Okay. So I brought the dt over here. Q over is it q over v? Yeah, q over v dt. Right. So that over there, and left the minus sign. Dt comes over because remember these aren't like this isn't fixed in this. It can move. And then we've got 1 over rho d rho. Okay? So I've just done some rearranging of this equation to kind of group units up and get the rho's isolated, right? So, does anyone know? So, what these then become integrals? Okay, so they become integrals, arbitrary integrals. There's no limits on them. Minus q over v dt. Does anyone know what this integral goes to? Remember, it's arbitrary, so there's no numbers involved. Does anyone know what that looks like once it's been integrated?
Negative qt over v.
Sorry?
Negative qt over v.
Yeah, you're right, yeah. And remember, there's going to be a constant, but I'm going to write it somewhere else. Okay, so there would be a constant, but because constants are constants, we can combine them into one constant. What about the right-hand side? This. Remember, this is going to be. What does this integrate to? Sorry? Yeah. Natural log of rho. Okay. What are we talking about next? Yeah, plus a constant. Actually, I am going to put the constant on this side, sorry. But yeah, remember that both of these would generate a constant because they're arbitrary integrals, and I've just grouped those into a single constant because it doesn't matter, right? If they're both constants, then grouping them into another constant is still a constant. Oh, hello. What's next on the list of things to talk about? So we need to get A, right? We need to get A out of it. So where A occurs when the density is equal to 0 and the time is equal to 0, right? Because, I mean, that's when the tank is full. Wait, what? Density is equal to 0? What the fuck am I talking about? No, density is not equal to 0. Ignore that. Density is equal to density 0. The original density, okay? That's why I said 0. My brain broke. So we can write, if time is equal to 0, this part goes to 0. So, because time is in here, just the whole thing goes to 0. So we get A is equal to ln of rho 0, okay? Yeah? So that's the constant. Now let's write that whole equation out. So we've got ln rho 0 minus qt over v, no, sorry, close those brackets, equals ln of rho, okay? And then we can move things around. So we can say that minus qt over v, I know it's late, I'm feeling it too. We'll be done soon. And then you can all run home. It's Friday after all. Yeah, so we got this. Does anyone know what this goes to? We can simplify this. Does anyone know how that works? Just a little mathematical trick. Whoa, hands. Yeah. Sorry? Yeah. So ln minus ln can be rewritten as this. You know, I'm not actually sure why it can be do that. I've never thought about it too much, but I might look that up when I get home. So we've got this, right? And now let's say because we've got this up here. Remember, I'm going to write this a little clearer because it's This is basically saying that the original density divided by the original pressure has to equal the. I'm going to write it like this, right? So this is saying the density at time t and the pressure at time t, right? At any time t is then constant, right? So that's so basically saying that the ratio between the density and the pressure has to be constant for any point, and so therefore we can say that the ratio between the density and the pressure at an arbitrary time t is equal to the density and the pressure originally, which are values that we have. Okay, so. I want to kind of isolate these on their own because remember we're making an equation and we want it to be as nice as possible. And you may recognize the form of this equation because I'm gonna exponentiate the equation. So I'm just gonna. Oh, sorry, my page is slipping. Qt over v is equal to rho 0. So all I've done is what have I done? I performed an exponentiation operation upon that, right? And that's removed the ln from this side, but added that to this side, which raises this into the index. Okay, we're happy with that? So in a way, this is kind of like a weird exponential decay of the ratio of rows, I guess. Well, it kind of makes sense, I suppose. And remember that we've got this equality up here, right? So we can write, if we rearrange this equality, we can actually write, I'm going to write it here, we've got rho, which way around is it? Yeah. P over rho, remember I've just inverted these, okay, is equal to PO over rho 0. And then I can rearrange these to say rho 0 over rho t is equal to, why have I written it that way around? Sorry. I don't have a rubber, this is frustrating. I'm gonna ignore this. I'm gonna write up here. Rho T. We're going to go back to that original form because I don't know why I rewrote it, but hey ho. Is equal to this. Remember that? That's a rho. That's a rho. Oh my god! Why do pressure and density have to be so similar? Two p's of the same pod. Then I can rearrange this, so I can write p0 over p. P0 over pt. P at any time t is equal to rho 0 at rho t. Wow, we got there in the end. Gosh, that's so simple. But yeah, so all I've done is taken that this up here, and I've just rearranged it. I'm not sure how well you can see that, but this is saying the original density over that is equal to the pressure over the pressure at any time t. The original pressure, the pressure at any time t. So I can substitute that in for that, right? So I can say, oh no, it should be the other way around. Oh well, I mean they're constant, right? So we can just flip them, right? That's all we're doing. Sorry, I'm getting a bit muddled. It's late. I've been busy all day. I've been in uni since 8. Let me have my failures. So we've got P. There's no T in this particular. Oh, fuck off, man. P over P0. Yeah. So we have an equation. We have an equation that relates the pressure. Wait a second. Have I done something wrong? What the hell? What is going on? Oh my god. Sorry, guys. No, I am correct. No, I am correct. Ignore past me, listen to future me, now present me. Right, and then we've got this, right? We've got this, and we've got this, and we've got this. Oh, well, sorry, no. We've got this, and we've got this, and we've got this, and we've got this. But we want this, we want T, right? That's what we want. So you can just use ln to extract that value. Do you know, like, so if I was to invert this again, like I'm going to write out because it's important. E to the minus. You can literally hear my brain just shutting down. It's you know when Windows just goes do like in the middle of something. That's what's going on right now. That's literally what's happening right now. P over P0, and I am correct in saying that. If we learn the whole thing, we go back to the original form that we had earlier. I'm not really sure why he's dancing around like this. It seems a bit unnecessary. But here we are. Ln P over P0. And remember, we've got this value. We're told that that's 1 kPa. That was the whole point. We're looking at how long does it take to go from 100 kPa to 1 kPa. And we've got this value and we've got this value. So all we do is rearrange the equation and put the numbers in. Are we happy to I don't need to do that, right? Yeah, cool. And you get time is equal to 3,542 seconds. Okay? Seconds. Oh, bloody hell. Okay, are we happy with what I've done there? Are we all alright with that? I know that was a bit of a messy one, but we got there in the end. I'll just quickly run through what we did, just so we can talk about it. So we had these values. We were asked to find 100 kPa to 1 kPa, how long it takes, given that this vacuum pump is pumping this regardless of pressure. We're told that the process is isothermal, which allows us to relate the thermodynamic variables, rho and p to this constant, and therefore we can easily write that the original density over the original pressure is equal to the density at any time over the pressure at that same time. Okay, and that's because there's a thermodynamic equivalence there. The thing is isothermal. Okay, that becomes a bit clearer once you've done thermodynamics, but it's given in the question, so just take it on face value. Okay. Then we use the mass continuity equation to say that the mass flow in minus the mass flow out is equal to the rate of increase of mass. And remember, we did some. I talked about some brief unit analysis that allows that to work out, right? And we said that there's nothing going into the reservoir. What's being pulled out mass-wise is the density times the volume being pulled out each second, right? Which is the Q. And I said that's the mass flow rate. And then I said that the rate of increase of mass is equal to, and remember that's negative in this case, but not generally it might not be. Not necessarily, it's not necessarily negative. And that's equal to the volume times the change in density over the change, the change in density with time, okay? So I wrote that equation out, and I rearranged it, and we did some integration. Remember that's arbitrary integration, there's no limits, so we got a constant out of it. In order to figure out the constant, we asked the question, what's the original density what does the equation look like when we have density equal to the original density at time equals 0? And that made this little bit here cancel out because it's got a t in it, and t equals 0, so bang, you're dead. And this ln goes to rho 0, right? So then we can safely say that our constant a is equal to ln rho 0. Then I put that back into this equation. So I said